So today we are talking about one paper focusing on automatic multi-step reasoning and tool use for large language models. This paper mainly focuses on how we can improve the step-by-step reasoning and prompting along with the tools when we construct the prompts for the LLM and how we can achieve that automatically. And this paper does not involve any fine-tuning at all, so it's all about prompting constructions. Moving next on the overview of this paper. So this paper first presents the automatic reasoning and tool use, so they call it ART. It is more like a framework about how can we generate decompose the problem step by step for the new task. And then the framework also allows you to manage. Basically, there's a tool library that allows you to create new tools and also allows the prompts, the generation process to select the most appropriate tools to use. For example, the search engines or the code generation or execution in each individual steps. And then given a new task, this method is going to retrieve demonstrations of a related task. So this is more related to the few shot prompting where you want to select similar task, right? Like how you solve the similar task, how do you generate these multi-step reasonings for the similar tasks in the past? And then you can include these examples in your prompts as the demonstration for the new task to generate. And the demonstrations also follow a flexible but structured query language. So it's like basically it proposes a framework of how we want to do the step-by-step formatting of the reasonings of the LLM. And then this encouraged the model to generalize from the demonstrations, although initially, they provide manual demonstrations to the LLM, but they also want to see how this framework can generalize to the unseen task, different from the ones that are demonstrated by humans. So this is I think it's a very useful framework. And also to understand this, I'm also going to introduce some of the related literatures for you to understand the concept. So this is examples presented in the art paper. So they have a task library. The task library, you can think of it as the few shot examples, right? So they figure out different types of task. For example, this is arithmetic task, so like math calculations. They can be a code generation task. They can be also a language reasoning task there. So they basically prepare lots of tasks and also the step-by-step reasonings and response to solve that task. So they're going to have like a task libraries that you can choose from to construct your prompts. And then given the task and the input, they're going to call a LLM into and decompose the task into steps. For example, the task is this, translated into a Peak Latin, and then it's going to formulate, it teaches the LLM to formulate the response into question, step-by-step question and response, right? So it's like Q1, and it figures out, oh, I need to do a search. I need to call the search tool first, and then it will, the yellow one is the tool output. So basically it passes a search query to the search tool, kind of like a search API, and then it will wait for the tool to generate a response over here, and then it's going to move to the second step in the reasoning process. Say the second step is generate code. So basically it will write a Python code to do this. And then the third step is like execute the Python code, and it will actually execute the Python code and get a response. And then the last step is basically like a dummy end of the question. and then they will respond the final answer to the task over here. So this is the template they use. So basically, it's like they have kind of a powerful LLM, which they use. I think in the paper they use Instruct GPT to decompose the task into multiple sub questions, as seen over here. And for each of the question, the response can directly be generated by a LLM, or it can be can call a tool like a search, generate code, execute code to get the response for each of the question, and in the end is going to get the answer to the question. Uh, because this framework is like interpretable, right, and it's very easy to understand, and so humans is also can easily change the program auto-generated over here. So, but for example, if the humans identify, oh, there's some missing line of codes in the automated generated programs, the humans can insert it in and then ask it to regenerate the full result to correct the final answers. This is the overview. And in the related work, they are fine-tuning. So basically, how can we improve the in-context learning for the large language models? One could be fine-tuning, but I think like fine-tuning, of course, will require lots of computing resources, right? But the literature shows that if we are able to fine-tune LLM, first, we want to scale it to train on an aggregated mixture of tasks, like a multitask fine-tuning, and also scaling the model size to a large set of parameters. And then it will achieve the state of the art for the in-context learning performance generations. The second is just prompting. The most famous one is chain of thoughts. So basically, like let's think step by step. So basically, there's a paper just saying if you insert the let's think step by step before your generation, you will improve the performance. So that's kind of the chain of thought style prompts. And then there's like an auto chain of thoughts of how we can leverage the prompts of let's think step by step and force the LM to use the chain of style of prompts so that they can improve the performance specifically in the math and common sense reasoning task. There's also papers published about tool use. Because as humans, we use tools, right? We use calculators, we use search engines. Same for the LM. So basically, they want to see, okay, can the LM, can we just prompt the LM and ask LM to figure out what tool to use, and we give them the corresponding API so that the LM can call the tool and then get the response and then improve the generation process. So this kind of that's a baselines, especially the auto chain of thoughts and the Toolformer. Here is the baseline comparison for the art paper. And I can briefly talk about what is the idea of the chain of thoughts, and also the Toolformer paper. So the chain of thoughts is like this, right? So it's just say you have a question, and then this is your answer, and then you just insert in that step by step. And then the LM will generate kind of like a rationale. The rationale is kind of the steps the LM will use to reach to the final answer. So basically, the LM starts to do some reasoning step by step, and then it will generate the final answer to the question. So there's like a zero shot chain of thoughts, just say insert let's think step by step. There's also like manual demos where in your prompt you can provide some demonstrations to the LM like about how human reason step by step over here as a in context learning examples for the LM, and then basically the LLM learns about, okay, what is the style, what is the format, and then it will tries to generate the rationale first, like generate the rationales before generating the final answer to the question. So that's chain of thought. So people have find that, for example, just ask the LLM, prompt the LLM to generate the steps, or like humans provide the steps to the LLM as demonstrations, and then ask LLM to generate output. And then the auto chain of thought is it trying to automate the process. So basically, it's trying to automate the demonstrations to the LLM. Like in the previous example, it's like human needs to write it ourselves in the demonstration. Well, the auto chain of thoughts, the idea is like, okay, whether we can call LLM to write these reasonings in the demonstrations. So that's the auto chain of thoughts. It's basically first cluster so this is kind of their question library. You can think of it as like a question library that you may have some answer already. And then they do a clustering so that the similar questions are grouped together. And then they prompt the LLM, like for example, select one from each of the cluster to make sure there's a diversity in your demonstration examples. And then they prompt the LLM with the let's think step by step so that the LLM kind of generate the demonstrations over here. And then for a new question, they just pull all of this generated rationales. Of course, they have done some filterings to make sure that the quality is good, right? So there will be some selection criteria to filter out the demonstration examples. And then they include all these automated examples in the prompts as the in-context learning examples for the new queries. So basically, you have a few in-context examples of questions, like similar but still diversified, comparing to the questions asked to the LLM. And then the LLM is going to learn about the reasonings, about the format styles, and then generate, again, like promptly with lessons step by step, and then it's going to generate the steps and along with the final answer is which number over there. So this is the idea of like auto chain of thoughts. Auto chain of thoughts is like ask the prompt the LLM multiple times. Yeah, to your previous question, it's like over here, it will use the LLM like queries multiple times to build your kind of demonstrations automatically. And then at the query time, you just directly pull them over here in the context, and then as your context in context examples, and then prompt the LM last time for the new question generated. And the second related is the Toolformer. The Toolformer, I think, is also very like straightforward to understand. I think if you use the chat, for example, if you use the ChatGPT now, you realize that ChatGPT may also have some Toolformer at backend, because sometimes you will see that it's circling, it's doing the web search, right, to get more context to your question. So the format of this is, for example, this is the prompt to the LLM, right? And then you ask it to call the API. For example, you can ask it to call like QA, and this is your question. You explicitly ask the LLM to do this, and whenever the LLM do this, like generate the QA, and then you can call your QA tool or search engine, right, to get a response from that. And once you get a response, the LLM can resume the generation again from that. So this way it can help enrich the context and also improve the generation performance here. So their idea is like you have a language model datasets, and then you can actually there can be like many different API calls. Like at the time of generation, the LLM may choose to use. You can prompt like kind of the LLM may choose to use different tools or different API calls, and then they generate the API calls and then select the best candidate that will minimize the loss of generation. like most likely response from the multiple cores, and then they will just insert it in the most likely answer from the search results. So the main difference is in the generation process. The LLM should be aware of what tool is available, how the LLM is able to call the tool while this specific format, right? And also at the generation phase, whenever the LLM generate this format, the the interface should be able to call the API or the tool and return the response. And then the LM will resume the generation all over again, like once this is generated. Uh, so about like what tools are available, so there can be like just a QA tool, like maybe it's just another LM for QAs, like for the common sense knowledge QAs. And also you can do Wikipedia search or Bing or Google search APIs. It can also do calculators of this, right? So if you do a calculator, you just pass it to a calculator, you are likely to get more accurate calculations than just ask LLM to generate a number. And also you can put the calendars or just machine translations. So this is all the related work. So if you understand that, I think then it will be easier to understand this paper. Uh, I think it follows a similar, some of those are similar. So first part is you want to figure out what to put in your context, in your prompt as in context learning examples. So that's why the art also create a task libraries. And in this, they specifically focus on this 5 categories of task. And of course, this framework can be extensible to other categories as well. But in this paper, they mainly focus on, for example, they think that these 5 common categories can cover majority of the task of the benchmark they want to test. And then from each of the cluster, they are going to create the demonstrations. In this paper, I think they create the demonstration manually. So basically, it's like you can randomly select. So for each of the cluster, you can randomly select a few tasks. And for that task, you can like human actually write the generations of how you want to solve this problem. For example, this is your problem, like they want to use Python codes, and the first step will be generate the codes, and then generate codes, and then there will be code execution, and then the humans will actually execute the codes in the Python environment, and then get the response over here, put the response over here, and then the last step is to get the answers. So basically, all of this demonstration is formatted by humans with questions, response, and third questions, response, etc. So this list of questions kind of also demonstrates the chain of thoughts to the problem. So once they have built the task library, so given the new task, so given at the inference time, right? Like given a new task, and this is the physics problem, and this is a physics problem, actual physics problem. And then they will call the LM to generate the step-by-step reasoning. So this will be provided as the in-context examples, right? So that the LM know, oh, what format I need to follow. I need to generate question. I'm also going to call the specific tool, and I'm going to get a response and then generate the second question and so on until I reach the end of question, which means that I have already reached my final answer. So all the green part over here, like these questions, are generated by the LLM, and then the orange part is kind of is the response from the tool, right? For example, over here, like the LLM figure, I need a search, or I need to generate code, and then it will send the kind of this sentence to the search or this sentence to the requirement to the tool API, and then it will execute the service API and get a response and hasten it back. And then the LM resumes generating the following up questions as the third step over here, and then execute the code and then get a response. So basically, this is a high-level framework about they are going to manage a task library. They are going to write these human demonstrations as kind of as the initial seed demonstrations about how to solve these different categories of tasks. And then at inference time, they are going to figure out, okay, what are the demonstrations I'm going to include in my in-context examples. And then the LM will start generating the step-by-step thinking along with this API call, right? So if it's going to call the search, it's going to use this format to tell the environment that I need to do a search or I need to generate code like that. And then the environment is going to call the tool, get a response back, and then the response is going to be served again as a context to the LM to generate the following up question. So that's the overview. And okay, and then the next is about the format of the LM generation. So basically, all the format is generated as query answer pairs. So it's like a question one, response one, right? Question one, response one. Question two, response two. So this green part. So it's like what LM needs to learn from the demonstration examples. And then in the end, if the generation is complete, it needs to put this dummy task to indicate it's complete and then generate the final answer from that. The IAM also needs to know if it's like a bracket, it kind of tells the tool name to call, right? And then in the answer, it should call the corresponding tool and get a response back from the tools. And interesting is the task library. It's about how they built this task library. It's from this dataset. It's from the Beyond the Imitation Game benchmark dataset, like a big bench dataset. This dataset is like a very, I would say like a more challenging dataset than just memorizing all the question and answers. Because this dataset like specifically focus on more of the reasoning task. So it's about like 200 tasks, and 80% of these tasks are kind of JSON. It's kind of like a list of inputs and targets, and 20% are just Python programs that they also allow the model to interact with the model over multiple query rounds of this task. And for art, I think they want to first reduce the scope to make sure whether the idea works or not, right? So they mainly focus on text classification and short answer generation. For example, as you see in the previous example, it's like a physics problem, and then the final answer can be very short. It's just a final number to that physics question. So they filter out the long generation task from the big bench and then get 91 task. And then they mainly focus on the 5 most used skills, like this arithmetic, code search, reasoning, and string operations. And that leave them about 50 tasks out of 91 tasks. And then when they build the library, they will randomly select 2 to 4 tasks from these five task clusters, and then humans will start the seeding process to write the demonstration programs. This demonstration is like this Q1 answer one, Q2 answer two, right? And then this is written by humans, and then they got the response from the corresponding tool. So this is all the initial task is like by humans, and then this will results a total of 15 tasks, kind of as a seed task, like compose the task library there. I think in the beginning it may seem small about it's like, oh, just 15 tasks, right? But once it is on and once they provide a flexible user-friendly interface for humans to interact and for humans to provide feedbacks and correct the programs auto-generated, they can easily increase the task uh, in their task libraries. So this is more like a framework of how they want to manage this task. This is their demonstration program. So when you like think about how the demonstration program looks like for each task, this is the example. So basically from here, this is the description. This is the question, and then this is written by human, like string. I need a string reformatting. I need a calculation, another calculation, and then that's it. So this is like the first demonstration, and then this is the second example with the second example for string that needs string operation, and then they will write again like Q1, response one, and these examples. And if at inference time there's like a string operation problem, right? They can choose from these examples as in-context examples to the LM. And then the LM knows, oh, at Q1, do I need to call? Maybe I can call a string function there, right? And then call the string. Each of these string function is actually a Python code function to get the response back. This is also about calculation. So most of the math problem, they formulated as a Python codes, just like a generate Python codes. And also they pre-store the math libraries, SciPy libraries, etc., like scientific Python packages at backend and basically demonstrate that to the LM and ask it to write the codes like that to do the symbolic calculations. And also they can use science libraries to solve equations, etc. Right? And then once it completes the codes, they just execute the code and get the final answers from that. They also present the chain of thoughts reasonings. It's like think step by step. So let's like just think step by step. And then this demonstration is like that's using step by step and then how it reached to the final answer should be yes or no, like how it reached the final answer is no or yes or which option is this? It's like a multi-choice problem over here. And then in their demonstrations, they show things step by step in the demonstrations. Show their thoughts regarding option A, show their another reasoning against option B, and then reach the final conclusion. So this is like demonstration examples to the LM that human crafted in the beginning. So once they created lots of these demonstration task examples, the next question is, given a new task, right? How can you select the relevant examples from the task libraries as your in-context examples? So basically they're going to, one is just performance-based. Performance-based is like if you have some labels already, like for the new task, say it's a string operation and you have 50 string operation problems and you know the answer to that. You have the labels already. You can just evaluate it. So basically they just iterate over the 5 clusters of tasks and just select a few programs from each cluster to compose the prompt as the in-context prompts to the LM, and then to see which cluster or which reasonings of each of the cluster can be, some cluster can be research, some cluster can be math, some cluster can be coding, right? And then they're going to see, okay, which cluster, which skills is most needed for the new task. And then they are going to use the demonstration from that cluster as the in-context examples for that. So basically the task cluster with the highest performance is chosen, and then they are going to use the demonstration from that task clusters as the in-context examples to the LM. The strategy two is use LM to select similar tasks. So basically you just ask LM. I think it's also related to the previous clustering. So that clustering does not require LM. Well, over here, they use LLM to identify similar tasks. So basically, this is a prompt to the LLM, like given two tasks. So this is the instructions, like how you can tell whether these two tasks are similar. And then you provide it like two tasks, task one and task two. And then you prompt the question, are they similar? And then the response should be yes, and the reason why they are similar. So this is your in-context example in your prompt, and then this is kind of a LM able to tell, okay, this is say task one is from your new task, and task two is the task in your task library, right? And so that you can compare whether there's any task in your task library is similar to the new task that needs an answer to. So basically, they use the LM to select the top similar task across all those task clusters, so that the in context examples can be across different task clusters. And when they benchmark the performance, they actually find that just using one task cluster seems outperform the LM-based task similarities. Uh, yeah, I think why? Maybe because the some of this problem is not does not require skills across different task clusters. So that basically, if you're able to save the task just focus on one specific skill and make that skill really good, it actually will make the performance well. Well, the LM-based similarity may be not that reliable, I will say. I think the key part is the LM-based similarity may be not that stable, reliable. Except for this simple one, the rest of the performance will or kind of lower than the just if you just focus on one using one task cluster, using the examples from one task clusters to as your in context examples for these questions. So that's the task. So the task is all about how we can identify relevant demonstrations as the in-context examples to the LM for the new task. So that's all the task library. And then there will be a tool library, right? The tool library is to actually provide the functionalities to the LM to call. So some of the basic service API can be search. So they use the SERP API. So this is like an API for Google search, like the SERP API. There's like a code generation, so they use Codex for the code generation, and also there's like a code execution. Uh, and also this is another example. Is like you can also like for example for string operation, you can also write lots of Python uh, functions as a tool, right? So if it's like a lookup or string split, string permutations, etc., etc. I think, yeah, I mean, if the code generation is really powerful, at some point it may not require all of this step by step. Uh, but if the code generation quality is higher, if you kind of identify a smaller task, right, like with a well-defined scope, then this will be helpful. Like the user another stronger LM to help with the reasoning, and then the code generation codex can just focus on with a very well-defined small code sections to execute. That may also work. So this page is actually about human feedback because the LM is actually going to generate like human readable programs, right? And then the humans can actually insert these additional stuffs or even add a new tool like a lookup. For example, I need a string lookup, and then they can write this lookup or maybe connect to a database lookup, right? So they can add these additional tools to the tool library so that they can connect that to the LM course. Uh, and once you are able to get the correct answer, this is going to be a new demonstration in your task library, right? So your task library is growing, and it's basically the platform is going to improve as you incorporate more and more examples, demonstrations in your task library. At the same time, when the users is able to add their own kind of tool or code functions to the tool library so that the platform generally will become more and more powerful, and also the performance will improve throughout the interactions with humans. And then the last is the experiment setup and the results. So I think this paper is published when the Instruct GPT is still one of the most powerful ones. I think right now there's far more choices than Instruct GPT. But in this paper, they use the Instruct GPT as a frozen LM to do the step-by-step reasonings. And then they use Codex as a code generation tool. And when given a new task, when they construct prompts, they select n task. So n like they set so they select like three tasks, and then they select two demonstrations per task. So in total, like six examples in the prompt for the new task as in context examples. And then this is how they measure the performance. So again, they measure the performance using the metric from the big bench dataset. So I think this is a very good dataset, also a challenging datasets to really test out the reasoning capabilities of the LLMs to make sure that it's really use reasonings rather than memorizations. So, and also it's a growing benchmarks, like it's generated by humans, the problems formulated by humans from hundreds of institutes, hundreds of institutes, and right now it's still growing benchmark. So I think this benchmark is very useful for to test out large language models. So along for each of the tasks, if you are going to submit a task to Big Bench, you also need to specify what are the scoring metric functions to evaluate that task. So basically, they just use the corresponding evaluation function and get it normalized between 0 and 100. And then they can do the aggregated performance for all the tasks they evaluated. Um, yeah, so they also compare to different baselines. So like a few short in context examples. So no reason provided, just like no intermediate reasoning provided, just Q&As without any reasonings. They compare to auto chain of thoughts. Well, the reasonings are auto-generated by LLM. And then they have the R tool. Art tool is like art, but without tool use. So basically art, if you think of art, you can still like without tool, you just use the Instruct GPT to generate the response to your each of the step. Right. So they want to turn the tool off just to see how much contribution is from the tool use and how much contribution is from the step-by-step reasoning part. They also have a GPT-3 best. These are the public best results, but these are not automated results because this may also include like additional human crafted prompts. And also using external tools to boost the performance. So basically, they want to see, okay, with this full automated prompting process, how is that compared to the best state-of-the-art results with human crafting and manually external tool using at that time. So basically, they compare to the state of the art. So this is a result they report. So it's like the few shot without reasonings, auto chain of thoughts with automatic generated reasonings. This is the art without tool use, and this is the art with tool use. And then this is deltas comparing to the art with tool use, right? So for each of the column, on average, comparing to the art with tool use, what is the gap there? So basically the smaller means that it's more comparable to art with tool use. For example, this is without tool use. So without tool use, you may see a drop of performance of 4.6%, comparing the one with tool use. And the few shot is like with art with tool use, you can see about 9%, 9% improvement. Um, comparing to like between few shot and art with tool use. So this is they also categorize into search, so like search related tasks, uh, math related task, and also chain of source coding and string related task over there. And this is the overall performance. So overall performance is like around 7.9%. So with tool use is able to improve the final results accuracy by around 8, a score of 8. Um, and comparing to few shot, and somehow the auto chain of sorts is not working over here. Yeah. I don't know, like the chain of sorts at the time of publish, it seems like they say like they improved the few shot performance, but at least on the big bench, so these are all the big bench benchmarks, it seems the auto chain of sorts is not improving over the few shot here. So this is a task library. They also evaluate the task not in the task library. So this is to test the generalizations of this framework over the unseen task. Again, like this unseen task roughly is still from these clusters, right? They will still require the search, arithmetic, and chain of sorts, etc. And then they are able to see what is the performance improvement over here and on this. So for example, for the search one, the improvement is like just 3.7%, but with the arithmetic one, the improvement is large comparing to the few shot and also comparing to the tool use. So basically it's like with scientific, especially for the scientific calculations, right? So with the tool, you will end up with a much better performance than just prompt the LM to get you a result for this type of questions. Yeah, I think that's very interesting to know. And comparing to the GPT-3 best, and also you can see like at that time state of the art with the tool for this scientific or math problems, they are able to also improve the state of the art. But for the others, for example, the code generation, chain of sorts, they are still behind the GPT-3 human crafted or human or other optimization technique. And another very common benchmark is MMLU, so language understanding benchmark. And again, they are able to show the big improvement against the few shot and also the GPT-3 at that time. Because some of the tasks, as you can see, also includes arithmetic ones, right? So this is like a huge jump if with tools, right? Either with the code generations, or you can call code generation, or you can like use all those powerful Python math, the scientific libraries to solve the problem. They also have some evaluation against the self-consistency. So the self-consistency is because, as we know, the LM is not deterministic, right? So depending on the temperature you set, especially depending on the temperature you set, if you prompt it different times, you may end up with a different answer. So they basically prompt the LM the same problem, they prompt it 15 times, right? And then they just choose the answer that gets like kind of the numbers that are consistent from the 15 times generation, and then they are able to see some of the improvements. There is about around like a score of three on average performance improvement across all the tasks. So basically, it's like if you prompt it multiple times and select the answer with most consistency, then that will probably be more like a probably be the most correct answer to that task. But I don't think, yeah, I don't know whether it's practical in practice. Like you prompt it so many times and just do an aggregation of that. But unless if it's like the accuracy is extremely important, right? And the score of three, actually it's about 10% improvement. It's like very critical. Then maybe some of this self-consistency technique is important under that scenario. If this about roughly about 10% improvements is like very critical for that scenario. And then of course they evaluate with human feedback. The human feedback is like you present the auto-generated programs to the humans, and then the human is able to do all type of operations to correct the programs, right? So they can add, um, for example, correct the steps like with the correction, add additional steps, or defining the new tools, etc. Right? And then they are able to see plus humans, like chain of thoughts plus humans, art plus humans. They are able to see a big improvement to that. So maybe that's the indication of LM can help improve the efficiency automation because humans do not need to write the program from scratch, right? So the LM is kind of give you a good beginning point for you to make this additional modification. And first, it will solve the current problem, solve the current task better, more accurately. And secondly, the human examples, like correct examples, will again as a feedback to the task libraries to help improve the general performance of the platform. So yeah, maybe that is a healthy um, ecosystem to build with human in the loop. Okay. The conclusion of this paper is it's first is like a very lightweight grammar of formats to the prompts to the LM, right? So you just format it as multiple questions, call the tool, get a response, ask the second question as such. So this prompting, this formatting is with reason of source with the tool calls and also the arguments in the generation process. And then they build extensible libraries for the task as well as for the tools, right? And then in the beginning, the programs like kind of human author programs, and when the platform is on, when the human in the loop to correct the programs, then there will be like a growing library of programs demonstrations to the LM. And also human can also help to build the tools for the LM. It can be external utility functions. It can also be very specific code, like a code functions that is efficient and that is commonly used for your task, right? To ensure the accuracy and consistency of the tool. And this is also an interpretable reasoning framework that allows humans to improve the task decomposition. So humans can modify, insert, or delete the steps in the generated steps, and also can add new tools to boost the performance. So I think this paper just describes a framework and a platform and how it looks like with human in the loop. And in the long run, when more and more when this platform is used to solve more and more tasks, and when humans are interacting with the platform more and more often to provide more demonstration and examples, it's going to improve. The platform itself is going to improve uh, in the long run iteratively. So I think it's a good format. It's a good format for how to combine LLMs and humans work together on the platform to improve the overall reasoning capabilities and tool use capabilities. Yep, that's all of it. And I'm open to any question or discussions.